This is Ideas Worth Exploring by Mark MacDonald. It's finally time to talk about climate change. I teased this episode almost a year ago when I talked about the different climates on Earth in the episode Building a Planet One Climate at a Time. But doing the research to figure out what actually is going on with climate change ended up being much harder than I expected. I know you've been waiting for a long time, so I hope you don't find this episode on climate change anticlimactic. Real quick, what's the difference between climate change and global warming? Answer: they're the same thing but with different connotations. The climate is the Earth's long-term weather patterns, and change means they're changing. But climate is really complicated, so people tend to focus on one number: temperature. A lot of the Earth's change in long-term weather patterns happens because of changes in temperature. So basically, climate change and global warming mean the same thing, but global warming has the focus on temperature, while climate change makes you think of the knock-on effects of raising the temperature, like sea levels rising and storm patterns changing. I'm going to use both words interchangeably, especially when one of them makes a better pun. Researching the science behind climate change has been very interesting for me because it needs a lot of physics and chemistry and biology and economics and politics and psychology to understand what's going on. So there's a lot to unpack. First, a brief story about refrigerators. I promise it'll be relevant. Then, we'll talk about the history of how global warming was discovered. Then, we'll discuss how the Earth's climate changes over time due to natural causes. Then, we'll talk about the greenhouse effect and how human actions have altered the natural climate patterns by releasing greenhouse gases into the atmosphere. Finally, we'll talk about how feedback loops make it really difficult to know how much the temperature will change, but we've started to get good at making computer models that tell us this sort of thing. And that's how this episode will end. But of course, that's only part of the story, so I'm going to make the next episode about why people are worried about the climate changing, including how it might make octopuses go blind. Then, a third episode will talk about some of the interesting scientific advances that we're using to respond to global warming. Yes, this is going to be a three-parter. There's just that much to unpack. So with that, let's talk about global warming. But first, refrigerators. Refrigerators take heat from one area and pump it somewhere else to keep your food cool. It's like making a little mini climate for your hot dogs so they don't grow bacteria. To get a refrigerator to work, you pressurize and depressurize a gas, and some gases work much better than others. Early refrigeration systems used gases that were toxic, flammable, or explosive. Then, in 1928, a man named Thomas Midgley invented a new type of chemical that was an excellent refrigerant gas that wasn't toxic, flammable, or explosive. This revolutionary new group of chemicals was called chlorofluorocarbons, or CFCs. And everything was great for years, until, in the 1980s, we started to notice that something was going wrong with the atmosphere. Ozone is a gas made of 3 oxygen molecules bonded together, and high up in the atmosphere, it usually forms a blanket over our entire planet that blocks a bunch of the sun's harmful ultraviolet radiation. But when CFCs started getting into the atmosphere from people who didn't dispose of their refrigerators properly, the CFCs ate away at the ozone, and a hole in the ozone layer started to form over Antarctica. Luckily, there aren't very many people in Antarctica. But if the ozone hole got bigger or spread to other areas, it could cause some big problems, giving people cancer and harming food crops. So, in 1987, 46 countries met in Montreal, Canada, and signed an agreement to stop making CFCs. And it worked! The ozone layer is recovering. It should be back to normal by 2040. Ozone layer crisis averted. I consider this one of the biggest success stories in international cooperation out there, right up there with the eradication of smallpox and the launching of the International Space Station. I wanted to lead with this example to demonstrate 2 points. First, that human actions can impact the Earth's atmosphere in major ways if we're not careful. And second, that when the whole world works together to solve these types of global problems, we can be successful. We know that global environmental problems can be solved because we've solved one before. Because climate change is another global problem that deals with the atmosphere. Whenever a cow burps, and whenever humans fly a plane or drive a car, it changes the composition of the atmosphere a little bit to trap heat near the Earth and make the temperature a little warmer. Today we're going to talk about the science behind global warming, what it is, what it isn't, and why, when you leave your car in the hot sun, it acts like a greenhouse and can get up to 40 degrees hotter inside your car than the weather outside. Part 1. History of Climate Science. Okay, let's back up a little. Way back in the 1800s, there were already a few people discussing the idea of global warming. In 1824, Joseph Fourier, a French mathematician and physicist, was interested in what determines the temperature of a planet. The obvious answer was the temperature is determined by how much sunlight the planet gets. But Fourier did some calculations and realized that if that was the whole story, the Earth would be a frozen ball of ice. But since the Earth isn't a frozen ball of ice, there has to be something else going on, and he realized that the something else going on was the atmosphere. The atmosphere acts sort of like a blanket to trap heat in, and that makes the surface of the Earth warm enough to be livable. We'll discuss the details of how this works in a minute, but it's called the greenhouse effect, and we should be grateful for it because it makes it possible to go outside in shorts and a t-shirt without freezing to death. Everything is well and good, and now we understood more about how the atmosphere affects the temperature. But then, in 1896, along came a Swedish chemist named Svante Arrhenius. Arrhenius realized that 1. Carbon dioxide is one of the main greenhouse gases that keeps the Earth warm, that 2. The amount of carbon dioxide in the atmosphere was going up because of people burning so much coal, and that 3. If you combine these two ideas, it means that human activity could make the planet heat up, which Arrhenius thought was a good thing. He reasoned that warmer temperatures would make crops grow more food and make some colder regions of the planet more habitable. Also, his ideas were purely theoretical, and they didn't have a good way to measure the amount of CO2 in the air at the time. They thought this warming was a long way away if it was real at all, so this idea was really only of academic interest. Years later, in 1958, a man named Charles Keeling managed to get himself a sweet deal. He got the National Science Foundation to pay for him to move to Hawaii and take measurements of the atmosphere on top of the Mauna Loa volcano. Keeling had developed a sensor to measure the concentration of CO2 in the atmosphere, and he used it to make measurements over the years, and found that the CO2 concentration was steadily increasing. Previous to this, a guy named Callender had shown that the Earth's temperature was also slowly increasing. It was clear that the temperature and CO2 were correlated, but at this point there was still a lot we didn't know about the atmosphere, and so it was too early to say with confidence that CO2 was causing the temperature change, or if maybe it was the other way around. But in 1967, two scientists named Manabe and Weatherald created the first accurate computer model of the Earth's climate. That's important, because climate is very complex, and a person can't really keep track of all the different variables in their head at once. But that's exactly what computers are made for. Manabe and Weatherald used their computer model to test what would happen if you doubled the amount of CO2 in the atmosphere. They found that it would raise the average global temperature by about 2 degrees Celsius, or about 4 Fahrenheit. More recent models say that it will be closer to 3 Celsius or 6 Fahrenheit. This showed that rises in CO2 concentrations really could cause the Earth's temperature to go up, and it gave an estimate for how big the effect would be. Manabe later won the Nobel Prize for his climate work. After this, better measurements of the Earth's temperature were taken using satellites. Better ways measure historical temperatures using tree rings and ice cores and rocks were developed, and more scientists started catching on that global warming was happening and was caused by humans. The evidence built up to the point where they had to start taking it seriously. In 1988, the United Nations established the Intergovernmental Panel on Climate Change, or IPCC, as a worldwide group of scientists, almost all unpaid volunteers, tasked with figuring out how much global warming is happening, what its effects are, and what we can do about it. Every 4 to 5 years, the IPCC publishes a report about what the world's top climate scientists know about climate change, and its reports are widely considered the gold standard of climate science. These reports have influenced the United Nations countries to sign a series of global treaties, like the 1997 Kyoto Protocol and the 2015 Paris Climate Accords, where the governments of different countries commit to doing things that will keep the Earth's temperature from changing too much. Except, it is really hard to get an international agreement like this to work, as we saw in an earlier episode of this podcast titled Society is in a Prisoner's Dilemma. Countries have consistently failed to meet the targets set in those agreements, and global warming is still happening. Which gets us to where we are today, with some people yelling that climate change is an existential threat to humanity, and others denying that it's even happening. And the issue has become so political that it makes people defensive to even bring it up, and this makes both sides ignore any evidence that they might be wrong, which makes my job harder, and I am left with only one option on how to do a podcast episode on climate change. Do good research, give clear explanations, be entertaining, and tell a lot of jokes. Did you know that metal expands when it gets heated? So as the Earth's temperature goes up, it makes the spacing between the rungs on metal ladders increase by a little bit. It's called climate change. Part 2. Natural climate change. You've probably heard of ice ages, where the Earth gets cold and covered in ice for a few thousand years before thawing again. Ice ages are an example of how the Earth's climate changes naturally over the years in regular cycles because of how the Earth's orbit wobbles. But that's over thousands of years. The Earth's climate also has smaller changes due to sunspots and volcanoes that are less predictable. But we've noticed that since the Industrial Revolution, temperatures have started going up, way too quickly to be orbital wobbles, and too steadily to be volcanoes or sunspots. To understand why this is out of the ordinary, let's start by looking at the Earth's natural climate cycles. 100 years ago, a Serbian scientist named Milankovitch set out to explain why the Earth has ice ages. Milankovitch realized that this mostly happens because the way the Earth goes around the Sun is a little bit wonky. Specifically, the Earth's orbit is wonky in 3 ways, which are called the 3 Milankovitch cycles, also known as orbital wobbles. First, the Earth's orbit around the Sun is not a perfect circle, it's slightly stretched out. And it turns out that the amount that the orbit is stretched out changes slightly over time, because we have noisy neighbors, Jupiter and Saturn. The way Jupiter and Saturn's gravity interacts with the Earth causes a cycle, where the Earth's orbit alternately gets stretched out and squashed. The second thing that's weird about the Earth's orbit is that the Earth is tilted. Yes, we've known about this for many years. This is what causes seasons. But did you know that the amount the Earth is tilted changes slightly over time? This is again due to the gravity of the other planets, and it makes the seasons more and less extreme in a regular cycle. The third thing that's weird about the Earth's orbit is something you might have noticed if you've ever seen a spinning top. The tip of the top, the axis around which the whole thing spins, seems to go around in a circle. This is called precession, and it happens with the Earth too. And as it happens, the North Star will move further away from north, and the Boy Scouts will have to use a different North Star to navigate as the Earth's axis precesses. When you put all 3 of these Milankovitch cycles together, they predict that the Earth should be cooling slightly over the next couple thousand years. So the fact that the temperature has been going up over the last couple decades can't be explained by the Earth's orbital wobbles. Let's keep looking. Sunspots are another natural phenomenon that can affect the Earth's climate. Sunspots are spots on the surface of the sun that are darker than normal. We've noticed that when there are a lot of sunspots, the sun tends to put out a little more energy than normal. The number of sunspots goes up and down in an 11-year cycle, which has to do with something about the sun's magnetic field. Someone out there on the internet could probably explain it if you care to look it up. But on top of this 11-year cycle, the number of sunspots also changes over longer time periods. We don't really know why, but we do know how much it changes by. Based on our best calculations, sunspot variations account for about 1/10 of a degree Celsius of the 1 degree of warming we've experienced in the last 150 years or so, or about 10% of the total global warming. So enough to notice, but not the main culprit. Finally, volcanoes can cause the Earth to be either cooler than normal by putting a bunch of ash into the air that can block sunlight from reaching the surface, or warmer than normal by pumping a bunch of CO2 into the atmosphere. But the recent trend of global warming has been steady, not what you'd expect from volcano eruptions, and the scientists who are tracking these things say that the amount of CO2 coming from volcanoes is 100 times smaller than the amount emitted by humans. So, natural causes don't explain the recent temperature rise. Let's look at human causes. Part 3. The greenhouse effect. If you want to understand how humans can affect the Earth's temperature, then you need to understand the greenhouse effect. I want to explain the greenhouse effect at a fairly deep level, but to do that, there are 4 things you should know: wavelengths, radiation, absorption, and equilibrium. The first thing is that light comes in different wavelengths, including visible light, ultraviolet light, and infrared light. The sun emits all 3. Visible light is the stuff you can see, ultraviolet is what gives you sunburns, and infrared is invisible, but you can feel its heat. And it turns out that it's not just the sun that emits light. The Earth does too, but it's almost all in the invisible infrared, which is why you can't see it unless you're wearing night vision goggles. So that's what you need to know about wavelengths. The second thing is thermal radiation. The reason the Earth emits infrared light is because all things give off light, as long as they're made of atoms moving around. It's called thermal radiation. I really want to get into why thermal radiation happens, but it's just too much of a tangent, so for now, you'll just have to believe me that there's some interesting physics behind it. As objects heat up, they emit more, and also in different wavelengths. Cool objects only give off infrared, but hot objects can also give off visible light, like a fire or a hot iron, and ultraviolet, like the sun. So that's what you need to know about thermal radiation. The third thing you need to know is the difference between reflection and absorption. When light hits a surface, the surface bounces some of it off like a mirror. It gets reflected. Some of it passes through, especially if the surface is clear like glass, which is called transmission. And some of the light gets absorbed and turned into heat. But here's the idea I want you to remember. When light gets reflected, the wavelength doesn't change. But when light gets absorbed, the object that absorbed it will eventually emit that light again through thermal radiation, but it will be in a different wavelength than the one that was absorbed. So that's what you need to know about absorption. The fourth thing you need to know is that the temperature can be found using a simple equation: energy in minus energy out. You have energy coming in the form of sunlight. Some of it gets reflected out to space, some of it gets absorbed by the atmosphere and then emitted back out to space, and some of it gets transmitted through the atmosphere and absorbed by the land and oceans, then gets emitted back out to space later. It's generally at an equilibrium. The energy coming in equals the energy going out, and so the average temperature of the Earth stays constant. But if something changes so that less energy is able to go back out to space, then the temperature of the Earth will go up. So that's what you need to know about equilibrium. With those 4 ideas in mind, let's talk about greenhouses. You know a greenhouse, the glass buildings that let you grow vegetables when it's cold outside? Let me tell you something interesting about glass. It's transparent. Isn't that neat? But it's only transparent to visible light. It blocks a lot of the ultraviolet and infrared light that tries to get through. That's why it's a lot harder to get sunburn through a window, though it's still possible. And that's also why greenhouses trap heat inside. The greenhouse lets light in, and when the light hits the plants or dirt inside, it heats them up. The hot plants and dirt then emit infrared light through thermal radiation. Out in the open, this infrared light spreads out, and the plants and dirt cool off again when the sun stops shining on them. But in a greenhouse, the glass traps the infrared in. It bounces back and gets reabsorbed by the plants and dirt, and everything inside stays warm. That's the greenhouse effect. Glass lets visible light in, but blocks infrared light from escaping. This is also the reason why your car gets so hot in the summer. The glass in the windows lets in the sunlight, but keeps the infrared from escaping. It's just the greenhouse effect. I have a shade that I put in my windshield after I park to reflect the sunlight, so my car doesn't become an inferno in the summer. But it would also work just as well to roll down your windows so that the heat can escape. But then you have to worry about car thieves and stray cats that might get into your car and pee all over your stuff. I mean that the cats pee on your stuff, not the car thieves, but I wouldn't put it past them. So that's the greenhouse effect. And it turns out that the greenhouse effect doesn't only work for glass. It also happens with gas. A greenhouse gas is a gas that traps heat. It lets some wavelength through, like visible and ultraviolet, but it traps the infrared. Some of the gases in our atmosphere, like carbon dioxide and water vapor, are really good at absorbing that infrared light. When a greenhouse gas molecule absorbs light, it makes the gas molecule wiggle around in a way that it doesn't like, so that a couple microseconds later it emits light again so it can stop wiggling. Half the time the newly emitted light travels out towards space, but the other half the time it travels back towards Earth, which is why greenhouse gases keep the Earth warm. That's the basics of the greenhouse effect. Greenhouse gases trap infrared light and send some of it back down towards Earth, keeping the planet warm. But there's also a lot of nuance to it that usually gets skipped over. I want to talk about one of those nuances, specifically how you'll get in trouble if you think of the atmosphere as being like a single sheet of glass. Greenhouse gases work differently from greenhouse glasses. To make a sheet of glass block more light, you make it thicker. To get an atmosphere to block more light, you don't need to, because most of the infrared emitted by the Earth that's going to be absorbed by the atmosphere is absorbed in the first 20 meters or so. Which I thought was really weird the first time I heard it, because if the atmosphere already absorbs all the infrared, why would adding more CO2 be a problem? When I tried to puzzle it out, I made the mistake I just warned you about. I was thinking of the atmosphere as a single layer. When you treat the atmosphere as many layers of air that can all be at different temperatures, the problem goes away. The temperature on the ground will be affected by the layer of atmosphere above it, which will be affected by the layer above that, all the way up until you get out to space. If you pump more greenhouse gas into the atmosphere, then the distance the infrared travels before getting absorbed goes down a little bit, and it's like you're adding another layer of insulation to the planet. This is known as increasing the optical thickness of the atmosphere. The takeaway from this is that you shouldn't picture a system where the sunlight hits the Earth and thermal radiation from the Earth escapes directly out to space. No. Instead, picture a system where sunlight hits the Earth, thermal radiation from the Earth hits the atmosphere and heats it up, and then in the upper layers of the atmosphere, the thermal radiation is released out into space. The other takeaway is that it's really easy to make a mistake when thinking about how heat moves up through the atmosphere. I didn't even mention the stratosphere or mesosphere or thermosphere that complicate the scenario I just described. And so you really need something like a computer model that keeps track of how all the different climate variables change. At least, you need computer models to understand how it works on a global scale, but the basics of it are easily testable in your backyard. You start with a pair of 2-liter soda bottles, partly filled with water, and put them next to a lamp. Make sure the bottles are the same distance away from the lamp. Then, in one of the bottles, you add a couple of Alka-Seltzer tablets, which you can get at any pharmacy. These will dissolve in the water and produce CO2. Cover both bottles and stick a thermometer in each one. Plastic wrap and rubber bands should work, but you might also need clay or a rubber stopper to get a good seal. Then wait 20 minutes. The bottle with the bottle without the Alka-Seltzer tablets should have gotten 1 or 2 degrees warmer because it was heated by the lamp. But the bottle with the Alka-Seltzer tablets will have gotten even warmer than that, maybe 4 or 5 degrees, because the CO2 in the bottle gives it more of a greenhouse effect compared to the other one. That's how you can demonstrate that CO2 is a greenhouse gas in your own backyard. It's amazing how much science you can do at home with 2-liter soda bottles. Now, we're almost done with what I wanted to say about the greenhouse effect. But first, I want to introduce the players in the greenhouse gas game. CO2, methane, refrigerants, nitrous oxide, and water vapor. The main greenhouse gas that's on everybody's mind is carbon dioxide, which is important because we've raised the CO2 levels in the atmosphere by 50% since the Industrial Revolution. Based on several independent lines of data, we can say with confidence that most of this increase in CO2 comes from burning fossil fuels, coal and oil and gas and stuff. Fossil fuels don't actually come from dinosaurs, though it would be cool if they did. According to Google, coal mostly comes from ancient plants, like trees and ferns, and oil and gas mostly come from ancient plankton and algae. So, if you've ever been tempted to lick a lump of coal to see what dinosaur tastes like, I'm sorry to disappoint you. CO2 matters a lot. It's the most important contributor to global warming, but I'm sure you already knew that. So let's talk about some of the lesser-known players in the greenhouse gas game. First, methane. Methane is a gas burped out by cows and also released by rotting garbage, and pound for pound, it traps over 120 times as much heat as CO2 does while it's in the atmosphere. But it breaks down in the atmosphere after about a decade, so that's kind of nice. But the thing it breaks down into is CO2. Second, refrigerants. The CFCs that were ruining the ozone layer once upon a time have been replaced with new types of refrigerants. But these new refrigerants are still strong greenhouse gases, possibly 1,000 times more of a greenhouse gas than CO2, and they leak into the atmosphere whenever someone doesn't dispose of their fridge properly. Luckily, many of these also break down after a few years. They don't accumulate for centuries in the way that CO2 does. Third, nitrous oxide, also known as laughing gas. This gets released when fertilizers are broken down by microbes in the soil, and it can last for over 100 years in the atmosphere. And fourth, water vapor. Water vapor is a strong greenhouse gas, much stronger than CO2, and the amount of water vapor in that the atmosphere can hold strongly depends on the temperature. As the temperature increases, the atmosphere can hold more water vapor, which amplifies the greenhouse effect and makes the temperature increase even more in a vicious cycle. So any small rise in temperature due to CO2 will be amplified by the increased amount of water vapor in the air trapping more heat. This is an example of a feedback loop that makes studying the climate so tricky. With that, I'm done talking about the greenhouse effect, and I'm going to move on to talk about 4 or 5 other feedback loops that either balance out or amplify the effects of adding greenhouse gases to the atmosphere. Part 4, Feedback Loops. Feedback loops come in 2 types, positive and negative. Positive feedback loops are like water vapor. They amplify the effects of raising the temperature. Negative feedback loops are the opposite. They balance out the effects of raising the temperature so that they're not as bad as they might have been. Let's look at some of each. First, the ice albedo effect. Ice makes the Earth more reflecty, so more sunlight gets sent back out into space instead of being absorbed by the ground. But, as the temperature goes up, the ice melts and less sunlight gets reflected, and that makes the temperature go up even more in a vicious cycle. It's a positive or amplifying feedback loop. Second, plants. CO2 helps plants grow taller and faster. So as the CO2 concentration in the atmosphere gets higher, the plants will grow faster and trap some of that CO2, making CO2 levels rise more slowly. It's a negative or balancing feedback loop. The plants help keep the balance, which is definitely something the Lorax would say. But there's a flip side to it also, because as the temperature goes up, it makes droughts more likely, and this can kill off the plants in an amplifying feedback loop. Third, permafrost. As the Arctic regions get warmer, the layer of frozen ground called permafrost thaws and releases a bunch of methane into the atmosphere, and also some carbon dioxide, which makes warming worse. That's a positive or amplifying feedback loop. But luckily, the methane only lasts about 12 years in the atmosphere before decomposing. But, unluckily, when it decomposes, it turns into CO2. Fourth, oceans. CO2 can be absorbed by the ocean, and higher concentrations of CO2 in the atmosphere will make the ocean grab more of it. The ocean is a big sink, a carbon sink. But it gets complicated, because higher temperatures make it so the water isn't able to hold as much CO2, and as temperature rises, the oceans release carbon into the atmosphere. So there's negative feedback as CO2 concentrations in the atmosphere go up, but positive feedback as temperature goes up. You get some of both with the oceans. Fifth, and I'm not sure this one really counts as a feedback loop, but it still belongs in the discussion here, is logarithmic saturation. CO2's warming effect becomes less significant as its concentration increases. As you add more CO2 to the atmosphere, the effect of extra CO2 decreases, which is great! Except, with the amount that CO2 concentrations are expected to increase over the next 100 years, the logarithmic saturation isn't going to be very significant. It really only matters for changes much larger than what we're actually expecting. But it can be comforting to know that if things get really out of control, beyond any reasonable expectations, the planet won't continue to warm indefinitely. The warming effect will eventually taper off. These aren't all the feedback loops we know about, and more are still being discovered. But the takeaway is that the Earth's climate system has many interacting parts. If you want to understand how burning fossil fuels will actually affect the environment, then you basically have two options. First, you can look at the data, measurements of how the environment is actually changing, the temperature and sea level and ice cover and everything else, without understanding all the mechanisms of what's going on. Or, second, you can create an enormous computer model that quantifies each of these feedback loops and how they affect the environment. Scientists have been doing both of these over the last few decades. They've made better measurement devices and also computer programs consisting of a couple 100,000 lines of code. You can look up the measurements on your own, but I want to talk a little bit about the computer models. Climate models simulate the physics, chemistry, and biology of the atmosphere, land, and oceans in great detail, and require some of the largest supercomputers in the world to predict what the climate will be like in the future. The IPCC, the United Nations-sponsored group that studies climate change, uses a set of 100 different climate models from 49 different research groups all over the world. These models each use different assumptions, and they're combined and compared with each other to see how human greenhouse gas emissions will affect the climate in the future. This suite of models is called the Coupled Model Intercomparison Project, or CMIP, but every time I read it, it makes me think of the word chimp. I imagine a chimp typing away at a computer to try to predict the amount of global warming. But I have been told that the scientists are actually quite a bit smarter than chimps, which is reassuring. The models used in CMIP aren't perfect. For example, clouds are really hard to model. Clouds are really important because they can either block sunlight or trap heat in, depending on how high up they are. Just as clouds affect climate, changes in the climate affect clouds. It's another feedback loop. And it turns out that writing computer codes that model cloud formation is really hard, because it happens on so much smaller of a scale than the global climate models are really tracking. Some researchers will just use a highly uncertain estimate of cloud formation in their models. The others will tweak the numbers that deal with cloud formation as a way to calibrate their models and get them to match historical data. The idea is that if they can get their models to match historical data, they can be more confident that they'll predict future outcomes as well. But it's a shame that the way they do it is by using cloud formation as a fudge factor. And I should note that calling it a fudge factor is not a criticism. As an engineer, I know just how necessary that kind of thing can be, but it would be nice if someone could figure out how to model clouds more accurately. Also, there's the problem of how we don't know what we don't know. We're still discovering new climate feedbacks. Even this year, there have been articles about how viruses can respond to climate change by influencing the way their hosts produce methane, in ways we didn't know about before. So our climate models are still not perfect, which is to be expected for something as complex as the entire planet. But we do know that 100 different models with different assumptions all show similar trends of warming due to greenhouse gas emissions. Conclusion. In conclusion, there are still many things we don't know about how exactly the climate system behaves. But one thing we do know with high confidence is that greenhouse gases make the temperature go up enough to be worrying. Other hypotheses have been proposed over the years for why the temperature is going up, but when we test them, they're always contradicted by the data, leaving fossil fuel emissions as the only hypothesis that matches our observations. So, that's it for today. The story of climate change will be continued in the next episode. Today we talked about the history of climate change and how it was discovered, the natural cycles of climate change the Earth goes through, and why it's different this time, the greenhouse effect and why it makes your car hot, some different greenhouse gases, and the feedback loops that can amplify or balance out the warming effects of greenhouse gases. With that, you now hopefully understand the science behind what is causing global warming. In the next episode, we're going to talk about why it's concerning that the temperature is going up a couple degrees, and how worried or not worried you should be. A sneak peek. Climate change may cause blind octopuses, lonely female sea turtles in your area, and potentially make our vegetables less nutritious. I hope you enjoyed this discussion of climate change. Come back next time for more science. You really don't want to miss the next one. Peace. This has been Ideas Worth Exploring by Mark McDonald.